Welcome to this video on equilibrium and supports. In this video, we will talk about two things. Number one, we will introduce the equilibrium equations, and we will show you how to include the forces and moments from various supports such as pin, clamp, ball socket, etc. I would also like to draw your attention to this textbook where you will find many solved problems, and also to this software which will help you solve statics problems. So what is static equilibrium? There are two kinds of motion. First is a translational motion where a body does not spin but moves from point to point. And the second motion is a pure rotational motion where the body stays at the same location but only spins. When a body has no translational acceleration, then the sum of all forces is zero. And when the body has no rotational acceleration, the sum of all moments is zero. And in a general motion, which is a combination of translational motion and rotational motion, the equilibrium equations consist of all the six equations, three sum of forces equations and three sum of moment equations. Forces and moments on a body consist of the loading that you apply, which includes weight of the body, the applied forces and moments, and the support forces coming from a ball socket joint, clamps, cables, rollers, wheels, contacts with floor, wall, etc., pins, bearings, and hinges. Find the forces and moments from all supports that keep the body in static equilibrium. There are six equations of static equilibrium of the body. We can find at most six support forces and moments. What is the strategy? For each support, count the number of support forces and moments that the support applies on the body. For forces, the point of application is important, and for moments, the point of application is irrelevant. Count the total number of support forces and moments, which should equal 6. If the total number of support forces and moments is not 6, then you will have to re-examine the support forces and moments. Sum all the forces, choose a reference point, sum all the moments at the reference point, and set the sums of forces and moments to 0 to find the support forces and moments. Let's first look at a clamp and a ball socket. A ball socket joint restricts translation in all three directions, X, Y, and Z. So a ball socket applies three forces and no moments. A clamp restricts translation in all three directions and also rotations in all three directions. So a clamp applies three forces, Fx, Fy, Fz, and three moments, Mx, My, and Mz. A cable and a roller. A cable or a rope restricts translation along the cable, does not restrict any rotation, and therefore it applies only one force along the cable. A roller or a wheel or a collar or a slot or a contact restricts translation perpendicular to the contact and applies only one force perpendicular to the contact, does not restrict rotation in any direction, and does not apply any moment. These are the examples: wheel, collar, a restricted motion of these balls along those wires, and this is a slot, and the slot applies a force perpendicular to the direction of the slot. This is another contact where the wall applies a force perpendicular to the wall on the ladder. A pin support applies three forces because the body is restricted to move in all three directions, does not restrict any rotation along the x-axis. So a body can spin about the x-axis, but a body cannot spin about the y and the z-axis. It can apply two moments. However, we do not want our pins to support any moments because that may damage the pin. So when the body is supported elsewhere, you should not include my and mz. A journal bearing restricts translational motion along y and z, so it applies two forces, Fy and Fz. It does not apply any force along the x-axis. When the bearing is aligned with the x-axis, it can apply two moments, but however, as before, we do not want a bearing to support any moments, so we exclude my and mz when the body is supported elsewhere. A thrust bearing restricts motion in all three directions, so include Fx, Fy, Fz. It can apply two moments, but we do not want it to, so exclude my and mz. A square hole bearing applies two forces, Fy and Fz. When the bearing is aligned with the x-axis, it can apply three moments, mx, my, and mz. However, we will exclude my and mz when the body is supported elsewhere. A hinge can supply three forces, Fx, Fy, Fz. When the hinge is aligned with the x-axis, it can apply two moments, but we do not want it to, so we exclude my and mz. The fundamental question is, we established that the static equilibrium of a body by setting force-coupled system to 0 at the reference point of our choice, which is O. But now the question is, does this ensure static equilibrium if we choose any other reference point A? The equilibrium equations for reference point O are these two. This is the sum of the forces. There is a couple mc acting, and at O, the forces F1 and F2 produce this moment. So the sum of moment is equal to 0. Let's take another point, A, and the equilibrium equation for reference point A is F1 plus F2 equals 0. And the moment at A should be 0, which is the couple mc. Then the moment due to F1 and F2, which we calculated as P1 cross F1 and P2 cross F2. And then we write P1 as this distance, fixed distance P plus R1, and we write P2 as P plus R2. And after a little bit of algebra, you can show that the moment the equilibrium equations are also satisfied at point A.